So this is our example for a one-tailed hypothesis test when we do not know the population standard deviation. Okay, it's going to make more sense as we go through it. But scenario: you're a scientist in a zombie apocalypse testing a new serum that might improve reaction times, which is very helpful when fleeing zombies. I don't know if you've ever seen those movies, but it's always the slow person that drags us down. You've developed a serum, and you hypothesize that it significantly reduces reaction time compared to the known average reaction time of unaltered humans, which is about 250 milliseconds. Okay, apparently zombie apocalypse is the only way you can get science funded, but I will leave that at the door today. We will follow all the steps we discussed in the notes. We'll go through step by step, and we can try to prove some really interesting stuff. So first is step one, and that is stating our hypotheses. If we want to test hypotheses, we have to know what they are. So first we have H naught. If you remember, this is our default, our starting point, the thing we're trying to find enough evidence to disprove. And that default is that the serum does not improve reaction time. So if it does not improve your reaction time, then our average reaction time would still be 250 milliseconds. If this was just essentially like saline solution, it's just not helpful to us at all. And so in math terms, we'll write that as H naught. Our default is mu, the Greek letter, is equal to 250 milliseconds. Okay, this is saying that the real average of people using the serum is 250 milliseconds. It's the same as not using it. Okay. Now, as we know, this is our default. We want to assume that nothing's happening as a general philosophy, and then find enough evidence to convince us out of that. And so our alternative hypothesis, H1, and you'll sometimes see HA for alternative, but I like H1 because it's like this binary of off until we can convince ourselves to be on. But H1, alternative hypothesis, is that the serum does improve reaction time. Okay. Now notice I don't say proves that it reduces the reaction time by a certain amount. I don't say that, oh, it's going to be 230 milliseconds. No, I'm just currently just trying to prove that it reduces our reaction time. So in math terms, I'll say that our alternative hypothesis is mu is less than 250 milliseconds. Okay, we just want to prove that it's less. We don't know how much less, but it'll be less. Okay, so these two are our hypotheses. Like I said, we'll start out not believing it works until we see so much evidence that we do believe it works. Right? So step two, we collect our data. Zombie apocalypse, it's pretty hard to find volunteers for serums that you just come up with in some kind of bunker. So we were only able to find 4 volunteers. Okay? Volunteer, and then reaction time. So we had some standardized test, milliseconds. We had some standardized tests to take these 4 volunteers and have them catch things and react to lights or whatever experiment that we set up. And we recorded their reaction time. So we have volunteer 1, 2, 3, and 4. And their recorded reaction times were 210, 220, 205, 215 milliseconds. Okay. So we collected the data. We're not drawing any conclusions about it. I mean, we can say it looks promising, but we haven't run any tests or done any math yet. But we have our data, and now we can move forward to see what conclusions we can draw. So step 3, something that we have a lot of experience with since week 1 and 2, and that's calculate the sample mean. Okay. The sample mean, the average of our sample, is something used in our calculations, and we can pretty easily find that. We know the formula in its really cool or scary looking form, depending on which side you're on. We have our big Greek sigma, I equals 1 to n xi all over n. Remember, this is just the sigma notation for we start with I equals 1 of our data point. So we start with x1, which is our first data point. And then this means we add it to the next iteration. The next iteration be I equals 2, which means this is x2, our second data point. And then we add that to x3, and then we add that to x4. We keep doing that until we hit n, our last data point. So this whole top is just a fun, fancy way to say we add up between x1 to xn, our last data point. So technically, we go from I equals 1 in this case to 4, because we have 4 data points. And then we divide that entire thing by 4. Okay? And what that looks like is our first data point, x1, is 210. Plus our next data point, x2, is 220. Plus 205, all the way to our nth point, our fourth point, 215. We add those up and then divide them all by 4, which, adding everything on the top, simplifies to 850 divided by 4. Or x bar, the average of our sampled data, is equal to 212.5 milliseconds. Okay. Now, some people might be convinced to stop here. We say, hey, average of 212.5, that seems pretty low compared to 250 milliseconds. It seems like we're already on the low side. Maybe that convinces you. I'm not convinced yet. I mean, we do have a very small sample for people, so this could be a fluke. And so we want to use statistics to see whether or not this is convincing enough evidence to update our beliefs from H naught to the alternative hypothesis, that it does in fact reduce reaction time. Because, for example, if our average reaction time, let's say we sampled 2 people and our average reaction time was 249 milliseconds, okay? First, that's not a major difference, going from 250 to 249 milliseconds. So we could say, oh, that's not nearly low enough. Also, just sampling 2 people, that doesn't make me feel super confident. So while we do see technically a difference here, we want to see that if it's a significant enough difference to statistically feel confident in saying that this does in fact improve our reaction time. That's all about hypothesis testing, is seeing if we have enough evidence to convince us of something new. Okay? So now we have step 4. This should be the start of the new math that we've been seeing, and that's calculating the test statistic. Test statistic. Okay, so we are going to find, and this is going to make more sense once you see the rest of this process, but we are going to find a test statistic. This test statistic essentially says, takes into account how many people we surveyed and how extreme the difference was, and then we can use this value to see if it's extreme enough to form our conclusion. Okay, this is a little hand wavy right now, but we'll see what that looks like. So the test statistic, which one you use, either the T version or the Z version, the t-score or the z-score, depends on whether or not we know the population standard deviation. Remember, we can think of the population standard deviation as if we have all of our data. You can kind of think of it as some measure of how spread out our data is. This would be a small, a very consistent set of data, a very small standard deviation versus a lot wider. Based on the math, you can kind of justify it as like the average distance your data is from the mean. So we have our average, and we can ask, oh, roughly what's the average distance from the mean is all of our data, and that tells us how squished it is. So if this was the actual measurement of our whole population, this being the average, there is a factual standard deviation for our data, but we don't always have access to that. We don't, like, if we're looking at heights of Americans, we literally just haven't done a census to measure every height in America, so we don't know the real standard deviation, the spread of the data. So we usually have to go through a sample. So the z-scores, sometimes we'll know. Things like IQ tests are calibrated to have a standard deviation of something like 15, but very often we'll have to use the t-score, because then we are not making that assumption, and we have to use our data to estimate the population standard deviation. So in this case, we don't know what the spread is. Quick moving magic splice real quick, just because I wanted to better explain this. So the standard deviation that we want to know is the standard deviation of reaction time. So in the population, we have the average reaction time, the actual population reaction time of 250 milliseconds. And we want to know the standard deviation. Wow, I'm so bad at drawing these. We want to know the standard deviation of how spread out these reaction times are, because obviously not every single person has the average reaction time. Some people might have above average reaction time, some people might have below average reaction time, and we want to know the standard deviation of how spread out this data is. Okay, so maybe for humans it's extremely consistent, and we can very well describe standard deviation as being really small, very consistent, or maybe with humans it's very wide, and sometimes it's hard to get a pin on this because the standard deviation will tell us how if our sample mean is somewhere over here and we have a small standard deviation, then it's going to be a lot more extreme and proof that our serum works than if we have a very wide sampled average right here, and then okay, that's then a standard deviation in. That's maybe not as exciting. So standard deviation is very important to know in this context because it tells us how certain extremes of values will help make us more or less sure in disproving our null hypothesis. Okay, we will do this calculation in the next video though. So because we don't know the population standard deviation, we're going to have to use the t-score. Okay, and all that requires is one extra step, and because we're not given the standard deviation of the population, we just have to estimate it. So to start with that, we refer back to our handy-dandy formula. The estimate of a population standard deviation is equal to the square root of fancy sigma notation again, I equals 1, and I know we've already covered sigma notation, but it's always good to have a little reminder, of xi minus x bar squared all over n minus 1. And we've already talked about how this n minus 1 is sort of like a bias correction to help estimate the population standard deviation. But so this is saying that we start with I equals 1. Look at that more like an I equals 1, the first data point, minus the average. Take that difference, you square it, and then you add it to the difference between x2 and the average and square it, and you keep adding through those. And then you divide it by n divided by 1, the number of data points we have minus 1. And like I said, we've done this 100 times yet, so this should not be new to anyone. So we start with the first data point, 210, minus the average we just found, the sample average, 212.5 squared, plus second data point, 220 minus 212.5 squared, plus third data point, 205 minus 212 squared, plus last data point, 215 minus 212 squared. And we divide all of that, still under our giant square root. This covers everything, not just the top. And n is 4. We have 4 data points, so we have 4 minus 1 in the denominator. Okay, we can continue to simplify this. So we say it's equal to the square root of, we find this difference in the square, and we get 6.25 plus this difference squared, 56.25 plus next group, 56.25 plus last one, 6.25 again. Great, and it's all divided by 4 minus 1, which is 3. So the numerator here simplifies to 125. That's what this all adds up to, over 3. So we can say that our estimate for the population standard deviation is, we're going to use these squiggles because we're rounding, so we're this means approximating 6.455 milliseconds. Okay, so this should be the last piece, because this whole section is to calculate the test statistic. And so we use this formula. The test statistic is t is equal to x bar minus mu over s divided by the square root of n. Okay, we just found the estimate s, so we literally have everything we can, or we need to calculate this now. So x bar is the sample average, which we know is 212.5. 212.5 minus the reaction time. This is, remember, because we're looking at testing if mu is, we know that mu of the human population is 250 milliseconds, and we're trying to prove that this reduces it. So this whole top part is saying, okay, if the human average reaction time is 250 milliseconds, that means we have a total difference in our sample. We have the regular, and then we have the enhanced serum version. We want to find the difference. How much did this drop our reaction time? And then we divide that by S, which we know is 6.455 milliseconds, divided by N being the number of data points, which is 4. Okay. This can simplify to negative 37.5 over 6.455 divided by square root of 4. Which simplifies to negative 37.5 divided by 3.2275. So all in all, our t-score is, we're going to use approximating again because we have decimals that we're rounding, negative 11.62. Okay, this is again a measure of keeping track of our sample size, our sample standard deviation, our and the whole difference that we attained with our serum. Okay, it's taking all these into account to give us a score to tell us how extreme our value was. All right. Now notice that as just a quirk, as n increases, as n gets larger, as we get a larger sample size, this whole fractional value should get larger. And so we can see that as the more people we have sampled, this whole value should get more extreme. Our t-score should get more extreme. So if we had 4 times our current number of people sampled, then this would be twice as extreme. So if we had 16 times as many people, this whole thing would be 4 times as extreme. Okay, and so as n increases, the number of people we sampled, the more extreme this value is, which means we're more sure about the effects that we see. Okay. So now we have our fun little t-score, how impactful our conclusion was. But this t-score isn't significant to us now. We want to see if this t-score is beyond a certain threshold. This is how extreme our results were, and this next step will show if essentially test to see how extreme we want our results to be to draw our conclusion that our serum is effective. So the next step is step 5, which is determine. I almost forgot how to spell. In the apocalypse, books are scarce, and so we sometimes forget how to spell. Determine the rejection region. It's technically based on significance level, which we've been calling alpha. So before I begin, I know we've covered significance and confidence intervals and all that jazz, but I want to emphasize this again. We can never be 100% certain about our results if we're making an estimate about the population. For example, if we want to sample a bunch of people to find the average height of the population, and we want to say, oh, I want to see if it's this value. So we measure a bunch of people. Without having measured everybody, we have to make an estimate. And the only way to, let's say back in confidence intervals, we cut off our tails and say, okay, this is the region I want to cover. This is we want to cover, let's say, like 95% of the values. So we cover the central 95% when we're doing confidence intervals. And so we snip off these tails as like the extremes that we aren't really considering. So if we're 95% confident here, covering 95% of the area, then we have our 5% distributed into both tails, so about 2.5% on each end. And this confidence is not a probability, which is very important, because the actual value does exist, but we want to be 95% confident that we've covered the real value. So if we did this experiment 100 times, this region should cover the actual real world value in 95 out of 100 of those experiments. Okay. Since I know we've covered that already, I am nothing if not long-winded about some stuff. But in this case, we want to use the same idea. We want to be 95% confident in something. And it doesn't have to be 95% confident. We could be 90% confident. We could be 99% confident. Those are usually the 3 most common values we see in classes like this. But let's say that we wanted our alpha to be 0.05. This means that we want to be 95% confident that we have the real value, and that those regions that are unshaded, those regions that we're not considering, that we're leaving out, is 5% chance. And we always have to choose a chance. The only way to be 100% confident is to say, like, literally we're covering every value. I'm 100% sure the average age of Americans are between 0 and 200 years old. But that That's not a useful estimate to us, really. So I want to be 95% sure we cover this. And so if we look at our confidence interval, I'm sorry, not our confidence interval, our distribution. We are doing a one-tailed test. Okay. Now remember our scroll weight. Look at all the beautiful writing we've done already. We are trying to prove that we are so extreme in dropping and in improving the reaction time that we can be sure. Okay. This is a one-tailed test. We can put our full 90 or our full 5% of uncertainty in the lower tail. Okay, so the rest of this would be the 95% of the area. Now we want to do this because you could technically run a two-tailed test, which we would take this alpha or its uncertainty and add it to both ends. Okay, so you will learn I am not consistent drawing these weird curves. So if we took this total 5% and we actually just divide it by both ends, so instead we have a 2.5% over here and a 2.5% over here. Our test could theoretically come up with the extremeness of our value, our t-score, to be right here. Okay, and so this could be theoretically the t-score we just calculated in the last step. And it's not extreme enough to be in our rejection region, the region where it's essentially testing if it's so extreme that we can reject the null hypothesis in favor of the alternative hypothesis. And in this case, let's say we take this 5% and we divide it by both sides, and we're just shy of it. And so our test is inconclusive. We fail to reject the null hypothesis, and then we keep looking into serum stuff. But we don't need to put any uncertainty over here. If we take this 5%, because we're not trying to see if it increases our reaction time, that's not something we're testing. If we want to put the full 5% on this side, suddenly we are in the rejection region. If we're only testing either a drop or an increase, this being obviously a drop, we just want to see if it has decreased our reaction time. And so we can put all our confidence to see, okay, we're testing if it's so extreme that it does decrease our reaction time. We don't care about looking at if it increases the reaction time. So we can put all of our significance and uncertainty into the lower region. And then suddenly we have a range of experiments that are suddenly able to overturn the null hypothesis. So that's exactly what we're doing here. We are seeing if our t-score that we just calculated, negative 11.62, is significant enough to reject the null hypothesis. Remember, we use a standardized normal curve that we discussed 2 chapters ago, which has a mean of 0. 0. That should be in the middle. And so our t-score is, let's just put it right here, t, which is approximately 11.62. Yeah, 11.62. 11.62. Okay, remember this is perfectly symmetrical. So we have our t-score that we just calculated, negative 11.62. And we want to, in this whole step, determine if it's in the rejection region. We want to establish what the rejection region is, what is extreme enough to convince us, and then see if our t-score of how extreme our experiment was, or the results in our experiment, and see if that's satisfying enough for us. Okay? So, to do this, we want to take a look back at the table we should have seen before. The student's t-test distribution. We can calculate this on our calculators, but sometimes it gets tricky depending on the version of your calculator. So sometimes we just use this to save us some calculator work and find out what we need to. Okay, so remember there are 2 elements for this. Unlike the z-score, this is multidimensional. We don't know the population standard deviation, so we need to get a little bit more information than the z-scores to draw our conclusion. And so the 2 dimensions we have are the degrees of freedom, and remember the degrees of freedom is degrees of freedom is nu, not mu, but this Greek letter nu, which is equal to n minus 1, the number of data points we have, minus 1. And because the number of data points we have is 4, then our degrees of freedom is 3. Okay? So we know it's 3. And remember, this is a whole chart that's describing the amount of area covered above this t-score. And so if we want to know the amount of area above, we're going to have to look at our degrees of freedom and the confidence that we want to be. And notice this is one-tailed. Now, so one benefit that we've already discussed again, I just like belaboring points sometimes, is that this is a perfectly symmetrical curve. Okay, so if we were to find our, let's say, our rejection region of how we want to be, T critical to reject, if we were to find it to be something like, let's say, 10 for this upper version, then if we find the negative of that, T crit equals negative 10. If we find the negative of that, then we can use it for the lower end. Okay, let me reset so I'm not confusing us for future calculations. And this will make more sense once I actually show you what's happening. Almost there. Okay. So we want to be, remember, we want 5% to be up here. So we want the upper tail probability to be 5%, and so that's here. This is our alpha. So degrees of freedom is 3. Alpha is over here. That is a t-score of 2.353. Okay. T critical equals 2.535. But wait, this was for the upper end. Okay, because this is perfectly symmetrical and we're trying to find the lower tail, we can just find the negative. So negative 2.535 describes the lower 5%. Okay? So, adding that back to a chart, here is T critical, which is negative 2.535. Okay? Now that is, remember, that is the line of how extreme a value should be to be confident that we can reject the null hypothesis. And so anything along this region is convincing enough for us to reject the null hypothesis. Anything less than negative 2.535. But wait, this is the value we just found, is negative 11.62. Okay, that is well within our rejection region, which is super exciting for the zombie apocalypse. So because our t-value that we calculated from our experiment, right here, because our t-value lies well within the rejection region, we can reject the null hypothesis. And so we can write that as step 6, our last step, which is interpretation. Okay, which we will say is we reject, I wish I could type on, I probably can't type on this whiteboard, I just haven't figured it out yet. We reject the null hypothesis in favor of the alternative hypothesis. And what that means in the context of our problem, and this is very important, is to move from, oh, we reject the null hypothesis in favor of the alternative hypothesis. But what does that mean for our conclusion? What does that mean for our experiment? And that's that we have strong evidence that our serum significantly improves reaction time making volunteers safer. Because remember, if you know statistics, you're going to be the most popular person in the zombie apocalypse. At least that's why I studied statistics.